welcome back to my channel. Today we are doing another calculus topic. So our big topic today is approximating with the tangent line. This is also called local linearization sometimes, mainly because this process I'm about to teach you allows us to approximate the value of a function when it's really hard or even impossible to just plug something in and get something out. So what this process is going to do is, no, that one does not work. So let's use a different color. So we can approximate a y value on a function by using a line that is tangent to the function at that point. Okay, so I'm going to demonstrate this visually. So here I have a graph. We have some kind of ellipse looking thing. It's not quite an ellipse, but that's besides the point. So we have this function, and let's say I can't just put a value in for x and solve for y, because maybe there's a lot of factors involved. Maybe it's an implicit equation and I can't separate my variables. There could be a number of reasons. So what we could do instead is actually find the equation of the line that is tangent to the equation at that x value and use that line to approximate whatever point this is, whatever the y value is here. So I'm going to go through two different examples using local linearization to approximate the value of a function. Okay, so now I am going to demonstrate how to use local linearization in this example problem. So we have 2, -2, and it's a given point on the graph of x squared plus y squared plus 2y equals 4. I sketched a little graph of that. It's a circle that's not quite centered at the origin. We're going to use the equation of a tangent line passing through the point 2, -2 to approximate a y coordinate when x equals 2.1 and x equals 1.9. So the first thing we need to do is find the equation of the line that's tangent to our graph. So we need to take a derivative. That derivative, we can then plug in the point that we know and get the slope of the tangent line. So first, I'm going to take the derivative with respect to x of x squared plus y squared plus 2y equals the derivative with respect to x of 4. We need to use a little implicit differentiation here. So the derivative with respect to x of x squared is 2x plus the derivative of y squared with respect to x is 2y dy dx. Don't forget your chain rule to tack that on. And the derivative of 2y with respect to x is 2 dy dx. The derivative of any constant with respect to x is 0. So now what I want to do is solve for dy dx. So I'm going to subtract 2x from both sides. And I end up, and I'm actually at the same step, I'm going to factor out this dy dx. So I have dy dx times 2y plus 2 on my left-hand side. All I did was factor out that dy dx is equal to -2x. Divide both sides by 2y plus 2 So dy dx is equal to negative 2x over 2y plus 2. So I'm not quite done yet, but this is one step closer to getting the slope of my tangent line. I'm actually going to erase this because I'm going to need a lot more room for this part of the problem than I will for the other part. Okay, so now I need to find the slope of my tangent line at the point 2, negative 2. So I need to plug that into my essentially slope equation or derivative equation. So I'm going to find dy dx at the point 2, negative 2, which means I'm just plugging in 2 for x and negative 2 for y. So I end up with negative 2 times 2 over 2 times our y, which is negative 2, so 2 times negative 2 plus 2. So that equals negative 4 in my numerator, then negative 4 plus 2, which is negative 2 in my denominator. Negative 4 divided by negative 2 is 2. So the slope of my tangent line at that point is 2. Okay, so the next step is I need to actually write the equation of my tangent line. And I can do this in point slope form and use the point 2, negative 2. So I have y minus negative 2 equals my slope, which is 2, times x minus 2. We can clean this up a little bit. So I have y plus 2 is equal to 2x minus 4. And then I will subtract 2 to both sides. It's not necessary to put this in y equals mx plus b form, but it might make it a little easier when we start plugging things in. So negative 4 minus 2 is negative 6, so y equals 2x minus 6. This guy right here is the equation of our tangent line. Okay, so I want to approximate this function when x equals 2.1. Now 2.1 is really, really close to 2, and remember, this line is right here. It's a line at this tangent point, or tangent line, or point of tangency, I guess I could say. And so what we could do is just plug in 2.1 to this line equation because it's so close. It's really, really close to where that point of tangency is. So I'm going to go ahead and do that. So we have y of 2.1, which is 2 times 2.1 minus 6, which is, so 2 times 2.1 is 4.2, and then we're going to subtract 6 from that. Okay, so 4, looks like we have negative 2, negative 1.8. All right, so we have negative 1.8 here. The other thing that we need to acknowledge, I guess, is that, yeah, y of 2.1 is equal to negative 1.8, but our function here is approximately negative 1.8. It's not exactly, so my coordinate isn't exactly 2.1 comma negative 1.8 for this function up here. It's approximately, it approximately has a y coordinate of negative 1.8. Now the nice thing for part B, which is why I moved my little squiggly over, is now that we already have our equation of our line, all we have to do now is plug in a new x value, which is 1.9. So we have y of 1.9 is equal to 2 times 1.9 minus 6. Okay. So it looks like, let's see, we have 3.8 minus 6. And so let's see, what do we have there? We have negative 2.2. So once again, y of 1.9 is equal to negative 2.2. However, the actual value or the coordinate on our function is 1.9 comma approximately negative 2.2. And if we graphed this equation and went right on the exact coordinate of 1.9, we'd be pretty, or we found where x equals 1.9, we'd be pretty darn close to negative 2.2. Okay, so now what we're going to do is move on to another example that also uses local linearization. Okay, so here is our last local linearization example. So in this example, we are given that if f of 2 equals 3 and the derivative of f evaluated at 2 is equal to negative 2, we want to use local linearization to approximate f of 2.01. So the first thing we need to do is find the equation of our tangent line. So we need to recognize that if I know f of 2 is equal to 3, then the coordinate 2, 3 is a point that is on f of x. Now, what f prime of 2 is also telling us, with that given piece of information, is that the slope of my tangent line at x equals 2 is negative 2. So right off the bat, we could already find our equation of our tangent line. So we have y minus 3 is equal to negative 2 times x minus 2. Using that point slope form, I'm going to clean this up a little bit just because it's a little easier to evaluate. So we have y, we're going to add 3 to both sides. Why not? So we have y equals negative 2. I'm going to distribute this as well while I'm at it. Negative 2x plus negative 2 times negative 2 is plus 4 plus 3. So y equals negative 2x plus 4, 7. Okay. So y equals negative 2x plus 7 is the equation of our tangent line. Okay, so now that we know that, we can plug in 2.01 to the equation of this tangent line to approximate f of 2.01. So let's plug in, so y of 2.01 is equal to negative 2 times 2.01 plus 7. Negative 2 times 2.01 is negative 4.02 plus 7. And so I think we have positive 2.98. So what this is saying is we have f of 2.01, which is approximately 2.98. And make sure you use the approximate symbol, right? Because it's not exactly 2.91. I mean, I guess it could be, but we actually just approximated this value using a tangent line. Okay, and that was it for today.